All right. Let's see along with this.
But the good problem, it was a good final project.
I feel like you guys had a piece of, like a 2-foot piece of round stock.
Did I tell you I have to make a sword in one of my classes?
Did you actually?
When I was a student, yeah. Ooh, yeah.
The main final project should just be making poof.
It wasn't even an engineering class. It was a Near Eastern Studies class.
That's so bad.
Scimitar? Or is it
No, it was modeled off in the Old Testament.
Second Reese's house coming up with the house. Is it Georgia or white and then
Okay.
herself?
So last week we talked about heat treat. Actually, we talked a lot about phase diagrams and TTT diagrams. Are there any questions over those diagrams before we move forward? No? Everybody feels like they're pretty comfortable with that material? Okay, so we left off with this slide. What is a CCT diagram? Anybody have any guesses before we bring them up on screen?
Continuous cooling?
Yeah, continuous cooling. And yeah.
So do you have a recommendation for how you actually go from a CCT diagram to a TTT diagram since they're so very similar?
Okay, so a TTT diagram is time temperature transformation, and it's done under isothermal conditions, right? So you're heating, and then you cool to some target temperature, and then you hold there for whatever time you're interested in, and then evaluate what you got, right? In the case of a continuous cooling diagram, this is where the cooling is actually is not stopping, but you're actually going to keep going. So the CCT diagram is actually the one that's going to be most useful in a sort of manufacturing situation. All right. So we talked. I'll kind of review slightly. Last week we talked about the equilibrium phase diagram, which gives us an idea of what phases we'll have present at various temperatures under equilibrium conditions. And we talked about how that wasn't really very applicable because we don't work in equilibrium most of the time. So then we brought in the TTT diagram. That gives us an idea of what kind of structures we would get under isothermal conditions. But even that, we don't really work in the isothermal world very often. So it's mostly this, what we're getting to now, where we're cooling things under some kind of a continuous or near continuous way. So this is what we're actually going to find is going to be most useful to us in manufacturing. But the other two are really good for getting the background and understanding the sort of the concepts.
You can convert from a TTT to a CCT, can't you?
You could get close. I mean, you could take a TTT diagram and just draw a cooling curve over top of it. But keep in mind that from the thermodynamic standpoint, if you're cooling and then holding, you have a lot of time for diffusion to occur and things to happen at that isolated temperature. Whereas if you're continuously cooling, you'll have a much more compressed time frame, and so thermodynamically speaking, things will happen differently, right? You don't have as much time for diffusion, and when you're continuing to cool, the temperature at which something transforms, may be suppressed a little bit. So CCT, as we already pointed out, and here's a more kind of a generic example. What we can see in this example, so we have this part here is what we would expect to see on the TTT diagram, right? In this case, it's just sort of the upper half. I showed one for a eutectoid composition 2 weeks ago where this came down and then it swept back over this way, right? So that's our TTT. And then here, these lines show you the cooling that you get under different kinds of conditions. So here we're showing what you would get for a water quench. This is maybe like what I would consider to be a polymer quench, something a little bit slower than water, but not as slow as oil. And then normalizing is an air, and then here you have cooling in a contained environment, in a closed furnace. So, widely differing cooling rates, and they give you just a generic idea of the kind of structures you might get. Again, this is just a generic example. We're going to show you some specific examples for particular alloys in a minute. Again, just like with our TTT diagram, this is time on a logarithmic scale. So here's one for grade 1040. This is a plain carbon steel, about 0.4% carbon. You can see here, again, this is going to show you the perlite. This would be your perlite or bainite nose here. And then you have all of the different cooling curves. And here, you'll notice they've assigned this so many degrees Fahrenheit per minute. So way out here, the slowest that they show you is 2.5 degrees per minute. All the way over here, you're at like 16,000 degrees per minute. So you can see this, it's quite a difference in the cooling rates depending on what you're doing. Of course, this cooling rate information is going to be a function of not only the media that you're using, whether you're dealing with water or air or some other fluid, but also how big the part is that you're dealing with and where in the part you're interested in. Cooling rates will vary throughout the part if you're dealing with a large part. So you can see here, on this one, we're at about 10 seconds. This is going to give you some martensite here. That ends with martensite. If I move to the next one, this is 4140. We can see out here everything is shifted over. The nose of the curve is shifted over substantially, and that means we have more time available to get to a particular microstructure, in this case martensite or bainite or whatever it is that we're interested in. We have more time available to work with to get whatever it is we want. If we continue on, if I'm going too fast, let me know. Slow down. If we move to 4340, so this is another alloy. So all three of these are 0.4% carbon materials, but they have different alloying elements. And you can see now on 4340, the nose of this curve is shifted over here a lot. Remember, we're back here around 10 seconds or even further back on the 1040. Now, we're orders of magnitude more time available to work with to get the same kind of microstructure. So I kind of said why this is important already. It's because in manufacturing, we have different fluids available, different ways of cooling, and different size components. But we really want to understand the material's potential. So I showed you three different alloys that all had different diagrams, and you can see that you had more or less time to work with depending on the alloy that you have. That is a way of thinking of that potential. You might remember from physics class the idea of potential energy of a little ball at the top of the hill, and when it's in motion, that's the kinetic energy. Well, in the world of metals, we have this potential, and we use the term hardenability for that potential. I'm going to jump forward a little bit more here. Hardenability is specifically the potential to become hard, and different materials have different hardenability. So we show graphically here a steel that is, we're measuring hardness across the diameter. We've got some diameter undefined here. We've quenched it, and now we're going to do a hardness test across the diameter. And if it's a large diameter, we'll probably see that the hardness on the surface is a little higher, or maybe a lot higher, than hardness at the center. So the purple, whatever grade that purple steel would be, you see it drops off quite a bit at the center. But the yellow, the steel represented by the yellow region, it still drops, but much less, right? So what we would say is that this steel that is represented by yellow has a higher hardenability than the one that's purple. They both have the same surface hardness, but the one that's higher in hardenability can keep a higher hardness to a greater depth. So this is important if you're trying to make a part that is going to have certain performance characteristics and it's some particular size. The engineers are going to say, well, we need to have some mechanical properties which are related to hardness at a particular region of the part. So they're gonna have to figure out what grade of material or what alloy of material will let them achieve that, that design criteria. So when we talk about hardenability, most commonly you'll see it referred to as ideal diameter. So the ideal diameter has a formal definition. It is the diameter of a bar which, when quenched in an ideal quenching, would have 50% martensite at the center of the cross section. Right? So this is a bit of a theoretical number. The nice thing about this is you can calculate this based on composition. So if you know the particular composition of some steel that you're working with, you can plug it into an equation and run a calculation, you'll get a number. So as a point of reference, the ideal diameter for a 1040 steel that we were just looking at is probably somewhere between 2 and 3 inches. For 4140, it's going to be around 4 to 5 inches. For 4340, it's going to be probably between 6 and 7, or maybe even a little higher inches. All right? All of that is a function solely of the composition. There are a few different ways that the calculation can be done. You'll find them detailed. The most common one is found in ASTM specification 8255. You might remember that I mentioned a fellow named M.A. Grossman, and I put a whole bunch of pictures in from his book in my lecture last time. We had all those different microstructures. He did all these studies on what happens when you heat and cool things in different ways. Well, he developed one of the early versions of this calculation technique, and it's still, that's what you see published in 1855. Caterpillar has done a lot of alloy development and heat treat development over the years, and they have a slight variation on the ASTM method. And so if you're working for a company that does a lot of work for Caterpillar, you will probably use their calculation. Caterpillar is, they will frequently specify the hardenability of the material that they want used in their parts, and you have to calculate it using their technique. There's another calculation called the Kramer method. I believe that was developed by somebody out of Bethlehem Steel. This is the one that Scott Forge uses. I don't know how we ended up with that one as our default method, but it's been that way forever, and we continue to use it. So they'll all give you slightly different results, but they're going to be similar, and they're all used in the same way. Some of them are, some of them do account for grain size, austenitic grain size, and some of them don't. Just that's the big difference there. So some more on ideal diameter. So alloys with the same ideal diameter do not necessarily have the same mechanical properties, right? And I'm going to illustrate that with two different grades here. These are UNS numbers. There's different ways of describing material. So there's the United Numbering System, that's what these are. There's the SAE system, this would be 4340 in the SAE system. So these are two different grades, and we have two different ideal diameters, one of 7.0, one of 9.5. The average yield strength of these two grades is a little bit different. And what I'm trying to highlight here is that this one here that starts with a K, it has a higher ideal diameter, but in general, its yield strength is a little bit lower. Okay? So the reason I'm pointing that out is because if you were only looking at the ideal diameter and comparing just that quantity of the two grades, you might say, well, I should be getting a higher yield strength out of this material. But in actual reality, we tend not to see that. So you kind of separate, you have to look at things a little bit independently. But if you're looking within the same grade, let's say I've got multiple heats of the same grade or very similar grades, these two grades are not very similar chemically. But if I had things that were pretty close, now I can look at the DI and I can compare and say, well, okay, that one's a 7 and this one's a 6. And I'm trying to get a certain set of mechanical properties for my customer. I think I'm going to go with the one that's a 7. Do I need to keep that slide up there? Folks are taking notes. Am I good to move on? I don't want to rush anyway. another way that we can measure and work with hardenability. You might already be familiar with this, some of you anyway. This is called a Jominy end quench test. So there was a fella, I don't remember his first name, but his last name was Jominy, and so this test is named for him. This is a very widely used test in the world of steel. And it, instead of just letting you run a calculation, it actually gives you an experimentally derived result. The details of how to do this test are also in ASTM 8255. It's got quite a bit of detail in it, and it's important with any laboratory type testing that you're doing. If you want to be able to make valid comparisons between one result and another result, whether that's derived all in the same laboratory or between laboratories, very important that you use the test method and use it accurately and precisely. And one of the things I'll point out is that in 8255, there are some minimum requirements for various things, but some of them don't have maximums. And so what I have found in my own work is that as I work with different labs, some of them, they typically all will do the minimum that's required, but some of them might do some extra that another one doesn't do. And if you're trying to compare results between two labs and one is doing a little bit different than the other, that can make it difficult to compare. So what I ended up doing was writing a document for Scott Forge that says when you're doing this test, here's how Scott Forge wants it done, which is in compliance with 8255, but also adds some additional details to provide more uniformity between various labs that might be doing that work. And you may find in your own careers that that's necessary for you to do from time to time. But the way the test works, before I get into the mechanics of the test, we have, this is copied right on 8255, we have different heat treatment temperatures depending on the grade and the carbon content. So the test consists of normalizing a little bar, heating it up, allowing it to air cool, and then reheating it and quenching it. We'll talk about how that's done in a minute. But the processing temperatures are given here. What we see is that we have basically up to here is covered by the top half of this chart, and then the lower half is down here. These grades here are all relatively low in nickel content, and these are high. And you may recall from our previous discussion that nickel affects the phase diagram, affects when austenite is stable, the temperatures of where the austenite phase field is stable. And consequently, when you're dealing with higher nickel alloys, you make adjustments to the processing temperature. That's what you see here. Again, just as a reminder, we have this generic phase diagram. We've got the start of your austenite phase transformation, and then where that's completed depends on carbon content in addition to nickel. So again, the specification takes that into account and has different temperatures depending on the carbon ranges of the alloys that they're working with. Yeah.
Is it quenching off some oil or water?
This one is always done in water, and I'll show you in a minute. This is always done in water. So here's a sort of a diagram of what a specimen looks like. This specimen is machined to 1 inch diameter. It's 4 inches long. It has a little bit of a lip on one end so that it can be placed in this fixture up here. And down below, which is not shown here, you have a little, just a little tube, and that tube is connected to a tank of water. And the way the specification reads is that when there's nothing in the way, the height of the water above that tube is what's defined. So that's how you, instead of having water pressure of so many pounds per square inch or something like that, they define it just by measuring how high the water shoots up above the end of the tube, and they define what that has to be. So you set up your system to get that result, and then you're going to be fine. But the idea is that the water hits the specimen on this surface only. It doesn't ever go up on the sides. It's only on the very end. And the reason for that is it allows you to extract the heat primarily from the end. And what that does then is it gives you varying cooling rates. If you're close to the quenched end, you have a fast cooling rate. If you're back here, you have a slow cooling rate. And so we're able to get a wide variety of cooling rates in one specimen. And once the test is done and the specimen is cold, you take and you grind flat surfaces 180 degrees apart, and you do Rockwell seam measurements from starting at this corner, moving back this direction, and you do them at 1/16 inch intervals. And you might even here at the university have a little fixture for doing that. There's the water, and there's an illustration of what the indentations look like. So each position has a different cooling rate. Now the really neat thing about this test is as long as you're working with a basic plain carbon or alloy steel, the cooling rate at J1 or J10 or whatever spot you're at is the same no matter what alloy you're dealing with. So you can have a fixed cooling rate, and you can compare how different materials respond to the same cooling rate using one very simple specimen. And here are the cooling rates that go along with not every specimen, well, not every position, but many of the positions. You'll see that in practice, you don't necessarily have to do every position, all 32 positions. A lot of times, the specifications for this are written to say do the first 16 positions or the first 12 positions, and then do, say, position 14, 16, then maybe 18, then 20, then 24, 28, 32. So they, as the cooling rates get slower, you don't necessarily have to do every spot, but you can. So here is some examples of the kind of results you would get. So we've got, I don't know, about 8 or 10 different alloys and actual geometry data from these individual alloys. So you can see what the range is. We can see a couple things. First, that some materials in the as-quenched condition, so at the position number 1, are relatively soft in comparison to some of the others, right? Now, it's important to note that the hardness at the J1, they call it J1 position, that first position that's tested, is really a function only of the carbon content. The rest of the alloying elements there don't have much bearing on what that hardness is going to be. And we can see that if you look at this brown line here, this is 1045, and if we compare that to, say, the dark blue line at the top, which is 4340, the 4340, you can see, I mean, the 4340 has a line that's not exactly horizontal, but almost, whereas the 1045 drops way off. But if you look at J1, they're not identical, but they're very similar. That's because carbon is the primary actor at that test look, at that specification. These over here, say this green colored one, this is the 4320, so lower carbon. The rest of the alloying elements are similar to what's in the blue 4340, but you see that the as-quenched hardness on the very end is quite a bit softer. So we see the effective carbon at J1, and then as we progress through the rest of the graph, we see how hardness is either fairly stable or not very stable, depending on alloy content. Questions on that?
Wait, so carbon content is a big factor, or?
It's a big factor in the surface hardness, right? And right here at the very beginning. But once you get below the surface, the carbon is less important. It's still important, but at the surface, it's the dominant variable. And when you get further in, it's not dominant anymore. I don't know if I have another graph, so I'm going to introduce this now. If it shows up in the graph later, that's fine. So a lot of specifications, both industry specifications and customer specifications, will define the geometry results that they want for the material to be used for certain parts. Now, if you look at the ASTM specification that does that, is specification A304. And it has a whole bunch of very common grades and then what the geometry curves should be. So they've got charts that look like this for each grade. And so you're not seeing 10 different grades on one chart, it's just one, but they do show you two curves. Every chart in there has two curves on it, a higher curve and a lower curve. And the reason for that is because when you order steel from a steel mill, you say to the steel mill, I want a specific chemistry range. You don't give them a specific number for each element because it's very difficult for a steel maker to hold to a specific number on every single element. So you always give them a range. Now sometimes the range might be pretty narrow, sometimes it might be wider, but you always give them a range. In the world of industrial specifications, they include ranges for all those in case the customer doesn't know exactly what they want. They still have ranges. You have to, you know, ASTM has a range for what 4340 would be if you're ordering into a specific document, right? So they then show you in the geometry hardness requirements both the upper and lower limits for the hardenability based on the typical range of elements for those grades, right? So I've only shown a single curve for each one based on results that we had in our, in our history and our data work. But if you were to go and look somewhere, you would, to see what's typical, you would see it expressed as, some lower curve and some upper curve. In the case of a customer specification, they may tell you just to work to the geometry curves that are in an ASTM document, or they might more commonly say at 2 points, they might say at J4 you have to be they might give you a maximum or a range, and then at some other point they might give you a range or min or max. But basically they'll define what they want just at 2 points. It's not very common that a customer is going to define an entire curve. They'll just give you the 2 points, which is a lot easier to work to. So we covered that about the role of carbon content. Oh, one other thing. So let's go back just a minute. This is kind of important. So here, if we start here and we look at the different grades and going up just at the J1 position, we would see that the carbon content is continuing to increase. But when we get to carbon over, say, about 0.6, the hardness at J1 doesn't really get any higher. So that is to say, if I had a 1080 or a 1090 or a 52100, and I quench them doing a geometry test, and I do a hardness check at J1, they're all going to be about the same. Because above 0.6, you don't see much increase in as quenched hardness. But what you do see, and the reason why we put more carbon in certain alloys, is that you get increased wear resistance. So for grades that are going to be exposed to some type of wear, a bearing, a gear, things of that sort, a cutting tool, they're going to tend to have higher carbon contents because they have better wear resistance. Okay. So why bother with the geometry or the ideal diameter? And the reason is because we have varying cooling rates during heat treatment. Now, we have, as I mentioned before, different fluids that are available to us. And we assign the fluids a thing called a quench severity number, which is typically designated with an H. And so you can see here what you get for typical H values for different fluids. What we're leading up to is combining the H value and the geometry information to allow us to predict what's going to happen with a specific piece of steel where we know the composition, how's it going to behave in heat treat before we actually get there. And I'll show you how that all happens in a few minutes. So we've got different H values depending on the material, the fluid that we're quenching in. So we've put a value, a severity, quench severity value on our fluid, and now we know the cooling rate at a specific geometry location. We can use that information to predict the cooling rate in a production part, whether that's a bar, a spindle, some shape. We can now begin to do some predictive work. And so here's a bunch of stuff that I copied out of a small little booklet, which I actually have with me, and I'll pass it around. This book is, I found probably to be one of the handiest little reference books for anybody doing metallurgy work. You can see my copy is quite well worn. This is called Practical Data for Metallurgists. It was published and is still available through the Timken Company. They've updated it from that particular copy. It's got all different kinds of information in it. So things like what's the typical composition of 5160 or 1080 or 4320, it's in there. Compositions of lots of other different elements. And then these curves, relationships between quench severity and geometry hardenability, that's where these come from. And they also have things in the back like conversion tables between Fahrenheit and Celsius, tables of weights and measures. So if you want to know how much a 4-inch diameter round bar weighs per foot, you can look it up in there. So just good practical piece of information. That book should be readily available. It's probably at about $15 or something like that. It's pretty cheap. Okay, so how do we use these tables? If I have a known quench severity, so that's what we have in this column, the fluid and then how it's agitated. So that gives me my quench severity, H value. And I know the size of the cross-section that I want to deal with. So I actually copied all of them from the book. So at the top, we have a 1/2-inch round, coming down and over, all the way up to 8-inch diameter, right? So if I know the quench severity of my fluid, and I know the size of the part that I'm dealing with, then I can predict what kind of hardness I'm going to get in various locations. So let's kind of walk through this. We'll take this one, this 3-inch round. If I quench this in oil with no agitation, that's going to give me this curve here, the H value of 2, all right? And at the center of that bar, I would have a hardness that would be approximately whatever you would get at J28. So I can go to the geometry curve for that alloy, whatever it is, look up J28, and that's about what I would expect to get for hardness. I can do the same thing at the half radius or mid radius location. That's typically where we do mechanical testing. And that's going to tell me that the as quenched hardness for that material would be about what we get at the J24 position. And on the surface, I would be at approximately the J, say 18 or 17 position, right? Now that's just one example. You can pick it for anything, any combination of quench severity and size up to 8 inches. These tables go up to 8. Yeah.
So you said no agitation.
Yeah.
How do you make these numbers work if you are agitating it?
So here we have 0.2 is oil with no agitation, and then we've got moderate agitation. Strong agitation in oil would be a 0.7.
Gotcha.
So let's just look at that one, right? So that would be this curve here, right? So if I had strong agitation at the center, that's going to be what, about say 13, the J13 position, right? And I could follow that curve all the way over to here, and at the surface for that, I'd have about whatever the geometry curve for J4 is, right? So if let's say I was doing this and I was going to compare say a 1040 and a 4340, right? Those two have very different geometry curves. So I could have the same bar, heat treated the same way, and I could predict what the approximate hardnesses would be for those two bars. I could use either the general geometry curves that are published in ASTM, or I might be able to get a geometry curve for that specific heat number from the steel mill. That's a pretty common thing to do.
Okay.
And so that gives me a little bit more precise understanding of how the material is going to behave.
What is the difference between moderate and strong agitation? Or how do you know when you've gone from
One to the
one
other?
agitation to the other?
Okay, so that's a good question. It's not defined very well, but in industrial practice, I'll just give you an example from Scott Forge.
Okay.
In my shop, I have 2 quench tanks. Each quench tank holds 50,000 gallons. One quench tank is filled with water, and one quench tank is filled with a water-soluble polymer. We don't use oil, so if I were gonna use, I would probably, the water-soluble polymer, their H values would probably be just a little bit less, or maybe a little bit more than what you have for oil, and not quite as much for water, right? It's kind of, at least our recipe of polymer kind of falls in between the two. In each quench tank, we have 8 shafts, 8 big motors, and a big impeller that's probably 14 or 16-inch diameter inside of a big tube that's got sort of a J shape to it. And so what happens is I can turn those propellers on and force the water or polymer to circulate in the tank from the front to the back. The tanks are long and narrow, and these are all arranged along the back wall of the tank. So I can make the water kind of circle this way, right? I can adjust the rotational speed of those impellers from nothing up to whatever they have for a maximum RPM, right? When it's at the maximum RPM, the surface of that tank is boiling and bubbling, and it looks like you put a surfing on it. Right? So that's obviously going to be strong, and somewhere in the middle would be moderate. Now, that's not very quantifiable in relation to these, right? I don't know how they did
It's going
it.
to change.
Say that again?
Because your cooling rate's going to change compared to those steps.
Sure, absolutely. So in practice, it's common that you would do experimental work to figure out where your specific system is going to be in relation to something like this. What you might do, what we've done numerous times, is to take a block or a bar and actually drill holes to various positions, like what we would show here, and embed thermocouples in there and then quench them. And then you can collect in real time that cooling data and see where you're at. Now, as it turns out, at Scott Forge, most of the things that we make are bigger than 8 inches. So these curves, for me, are not as useful as they would be for somebody who's, say, doing automotive components, which is really where this kind of was geared at years and years ago, when they were making smaller, and they still do use a lot of small steel parts in automotive, like trucks and things like that. Right? The world of big stuff is much smaller than the world of smaller stuff. So what we would do is do an experiment, a physical experiment, look at cooling rates, and then look at our historical data. We might look at some of these as well. Right, yeah, so you can still use it, it's just, you got to do a few extra steps to get there. Yeah. Any other questions? Okay. We kind of covered that, looked at that already. That. There's some other charts. These are a little bit different than the ones I just showed. Here, what they've done is they've taken multiple things and put them all on one chart, right? So we have oil quench, mild water quench here, and air quench here, and they've laid everything out on one chart. The idea is that you can still get the same understanding of material behavior, but it's just presented in a different format. Okay. I want to stop there for a minute. Should we take a 5-minute break, or should we keep going? Because I'm kind of changing subjects here, and if you guys want to take a little break, we can do that.
What do we do with the test?
What?
What do we do with the test?
Whenever we're done with lecture.
Okay.
So,
Let's take a break after the lecture.
take a break after lecture?
Yes.
Everybody good with that? All right, okay, good, all right. So, changing subjects a little bit. So we talked about hardenability, why we use it, how we use it. Let's cover the different types of heat treatment operations that we have. I'm going to group these into 2 different sections. The first is operations that are performed where we're heating the metal above the AC3, so it's fully oxidized. the second group is operations where you're not going above the AC1, so you're not austentizing at all, okay? Annealing, and I should probably call this full annealing. In the world of terminology, and ASTM, for example, which is the organization that sets a lot of definitions for these terms, they have the word annealing, and then they have a whole bunch of subgroups of what variations exist on that. What I'm talking about here is what would be called full annealing. This is where you're going to heat something up to it's fully austenitized, and then you're going to cool it very slowly, right? And the idea, especially in the world of steel products, is that you're going to get a pyrolytic structure. It'll be soft, it'll be easy to machine, it'll be easy to do cold deformation if you're doing, say, a bending or a drawing operation on. This is an operation where diffusion is what's driving microstructure change. It's something that takes a long time. Typically, it's done by heating your product up and then shutting the furnace off and just leaving the furnace closed so that things can cool slowly over a long period of time. This one is the one time where you're going to see equilibrium behavior. We have a variation of this called spheroidized annealing. This is used for steels which are hyper-eutectoid, right? And these are, this process is used to form the carbides into a sphere. The hyper-eutectoid steels, if cooled slowly in a full annealing type of a process, will tend to form carbides along grain boundaries in addition to whatever pearlite is formed. The carbide along the grain boundaries, we often refer to it as a network carbide, and it's very brittle. And it means the part itself is very brittle. So we typically don't want that to happen. So for those parts, if we're not immediately going into a fully heat-treated condition, fully hardened condition, we would go into what's called the spheroidized annealed condition. And so that allows the extra carbon or carbide to form a spheroidal shape, and now you don't have the brittleness issues that you have with the network carbides. And so again, then this material tends to be relatively soft, it's machinable, formable. Any questions on those two items? Okay. So normalizing is another operation in which we heat fully above the AC3. We hold for some period of time, allowing diffusion to take place, making sure we got all of the transformation to occur. And then we open the part, or open the furnace, and we typically will take the part out of the furnace and allow it to cool under ambient conditions. You may use a little bit of accelerated cooling, say with a fan, for example, but generally you're not cooling exceedingly rapidly. But it's faster than in a full anneal. And so you'll still get usually a pearlitic structure, but in this case your pearlite will be a finer pearlite. You'll have a little bit higher hardness than when something in comparison with a fully annealed component. Your tensile strength will be a little bit higher. We see that in certain situations customers use parts in the normalized condition. Sometimes you will combine normalizing and tempering, which we'll talk about in a minute, to get a particular target value for hardness or strength. Normalizing is also used as a preliminary heat treatment step prior to a fully austenitizing and quenching step. The reason for doing it in that circumstance is to help get a small grain size. We've talked about grain size a few different times in class, but I think it's been a little while, so we'll review it here. When you are at a high processing temperature, whether that be forging or rolling, you're well above the AC3, and you're also above the temperature at which elements that form grain refining compounds like aluminum nitrides or columbium carbides or vanadium carbides, you're above the temperature at which those constituents are present. And that means that the austenite grains are free to grow to quite large sizes. That's fine when you're doing bulk plastic deformation, forging, rolling, no problem there. But you don't want that large austenite grain size as the precursor to your heat treatment, because the large grains, the large austenite grains, tend to result in low toughness, low ductility. So we want to get a smaller austenite grain size. So we use normalizing to do that. And the way that's done is you fully austenitize the part, but you don't go to such a high temperature that you begin to dissolve those constituents that act as grain thinners. That means that when you nucleate new grains, which is going to happen when you go through a phase change, you're going to nucleate new grains. They're going to grow, but they'll only get as big as they can based on the distribution of the grain thinning constituents that are there. So that allows us to sort of reset the grain size before we go into the rest of heat treatment. That way we start off with a small grain size. For those who have had a chance to do grain size studies, look at grain size, you'll see that typically in the world of plain carbon and alloy steels, customers are looking for grain sizes on the order of approximately ASTM 7. That's anything smaller than 5 is typically considered fine grain, and is usually acceptable for most industrial applications. Sometimes they'll go a little smaller than that, like a 7. Can anybody think of a situation when a customer may actually want a large grain component? Not with necessarily these alloys, with other stuff.
I mean, if you're, talking about like turbine blades, they actually want a single crystal, that's just because you don't want creep to occur with high temperature, high stress that parts undergoing.
Right. So a single crystal is the best example. That's the biggest. But even in things that are multi-crystalline, you still will find that you'll get less creep with bigger grains. So any application where you're at an elevated temperature and you need to maintain dimensional stability will be benefited by having large grains. That's the one exception to what I had said previously. Okay. Any other questions, comments? So the next process that we get to is quenching. And by quenching, I mean the combination of austenitizing and then cooling. This process is very similar to normalizing initially in that you're heating up to a fully austenitized condition, and you're also making sure that you don't heat higher than the temperature. You're not going so high in temperature that you dissolve the grain thinning constituents. Generally, you're going to use a slightly lower maximum temperature for this austenitizing cycle than you would for the normalizing cycle. The reason is because when you go through this austenitizing cycle, again, you will nucleate brand new austenite grains. And if you keep the temperature a little bit lower than you did in your normalizing cycle, those grains will stay just a little bit smaller. And so it's a way to get a continued refinement of the grains, which is going to give you an enhancement of most of the mechanical properties. Once you've completed the austenitizing cycle, we now have to quench. And instead of cooling in air as we would for normalizing, we're going to cool in some type of a fluid. And we talked about already, there could be water, there could be polymer, there could be oil, there could be a brine. In some cases, it could be molten salt. There's a lot of different options that we have available. The idea is that we're cooling fast enough that we suppress diffusion and we get microstructures that we can't get with slower cooling rates. And it looked like you had a question.
Yeah, so assuming you have different like austenitizing times, you get different grain sizes, how would that affect your properties if you have larger grains versus smaller grains than you quench?
So, a few different things we want to try to address in that question.
Yes.
First part, if I have different hold times at the same temperature, do I get different grain sizes? Right, that was kind of the first part of your question.
I mean, assuming that you do.
Well, you don't.
Okay.
You wouldn't, because you haven't dissolved the grain pinners. Grain pinners and their distribution is what fixes the grain size. So as long as I stay at a temperature where they have the same number and distribution of grain thinners, grains won't get any bigger. Right? Most of the grain thinners, aluminum nitride being the primary one, doesn't dissolve until you get over about 1800, maybe 1830 degrees. So as long as you keep your temperature under that, you will always have aluminum nitride. In the case of the steels that I work with, you'll always have aluminum nitride present to serve as a grain thinner. The activation energy that I put in thermal heat will determine what grain size I get, provided I have grain thinners present. So if I go to 1750 in my normalized, I'll get one grain size. If I come back and austatize the second time and say 1650, I'm 100 degrees lower, there's less energy, so the grains won't get quite as big. And that means they'll be a little bit smaller than they were after the normalizing cycle. The hold time is not going to affect the grain size because the grain thinners are what controls the grain size. The temperature and the distribution of grain thinners are what control the grain size. But I do get some changes by extending hold time where I can, in that I may, with a short hold time, I may not fully dissolve other constituents, other kinds of carbides, or other things that are in there, so iron carbide or chromium carbide or something like that. I may not fully dissolve all that with a short time, so it might be beneficial for me to go with a longer time up to a point to make sure I get as much of the carbon and alloy elements in solution as I can before I go into the quench. And the way that we would see that in practical effect is that I would have a little bit higher as quenched hardness and higher resulting tensile and yield strength. Did I fully answer all your questions?
Yes.
Okay. Because you had several parts, I want to make sure I didn't leave
Yeah.
anything out. All right, so quenching typically doesn't allow time for diffusion to occur. This is especially true in small components. Now, some of the time, some of the things that I deal with that are quite large, you may not be able to cool it fast enough to completely prevent diffusion from happening. And so in those circumstances, based on the drawings and diagrams that you've already looked at, I'll end up with a mix of structures. I might have some martensite and some bainite, maybe some bainite, some perlite. It's just going to depend on the alloy, the size, and how I cool it. But it's not uncommon to see mixed structures, especially as I look at different regions of the part. If I look near the surface, I'm going to tend to have more martensite. Near the center, it's going to be something a lot less martensite. It's important to note that during quenching, you tend to have a lot of stress developed, and that can lead to cracking. So one of the things that I deal with in my job is looking at parts that crack and trying to understand why they crack. Sometimes that's related back to the stresses that develop during heat treatment. Sometimes it's other reasons. These stresses can be magnified with different types of geometry. And so it's quite important that as we look at what we're going to quench, we pay attention to the geometry and we're careful, especially with corners, especially inside corners. Sharp inside corners are stress concentrators, or stress magnifiers, especially during quenching. And so we have to be careful that we avoid having those during the quenching operation. The part may need them, but they may have to be machined in afterwards. The other thing that can be a source of stresses is not only corners, but just big changes in dimension. So if I've got a thick section right next to a thin section, there can be a significant amount of stress developed during quenching between those two. And so you have to see if it's going to be a problem or not. This may or may not be a problem because you've got different alloys that are going to get different microstructures present based on how they're cooled. So I can make two parts of the same geometry, one out of 1040 and one out of 4340. I may have cracking problems with one and not the other. I may, in fact, had a conversation with a customer this morning that's having a cracking problem in some 4140 parts, and they are occurring in areas of near varying thickness changes of the part. one of the solutions was to consider using a 4330 or a 4340 material. Now, that might be a little counterintuitive because we know from our previous discussion that those grades are higher in hardenability than a 4140. They are. However, those grades also are higher in nickel, which is going to improve the toughness in addition to the hardenability. So that could be a viable solution to this customer's problem. That particular solution has a cost implication because you're using something that has a nickel as an alloying element. Nickel's one of the more costly alloying elements, so that might not be the first choice. There may be other ways that we can go about looking for a solution for the customer, but it's certainly one that's under consideration. I think I showed earlier, maybe I didn't, we'll get to it later, but today we have modeling tools that allow us to predict what kind of stresses we're going to have during quenching. Now, interestingly, this particular customer example I just gave you, we did do the modeling, and there was no suggestion from the model that we were going to have a cracking problem. And yet, there's a bunch of these parts that are cracked, and we know that the cracks occur during our quenching. So the models are not 100% effective. As with anything related to computers, they're only as good as the inputs, and you're always working to make those inputs better. So that's what will happen. We'll take these parts, we'll cut up one or two of them, try to better understand what was the initiation point for the cracks, and then how we can tweak our model to predict that more accurately, and then figure out how to change the geometry or change the alloy to eliminate the problem. Or maybe change the quenching practices. Sometimes instead of quenching all the way down to some low temperature, you quench down to a temperature that's right near the martensite start temperature, or maybe just slightly above the martensite start temperature, and then put the part in the furnace at that temperature to allow everything to kind of even out thermally and stress-wise before you bring the part down to its final temperature. That can be a good solution. I think we talked about that. We called it MAR tempering. I think Dr. Metzloff gave a couple of examples he was familiar with where that can be used. And that is sometimes a great way to alleviate this problem. Moving on. Once we've got something quenched, we're going to just make the assumption that we have a highly hardenable component. We have developed a fully martensitic structure. Now we have something that has a lot of stress. It's very high in hardness. Maybe it's, say, Rockwell 62 or 65 if we've got enough alloy content. That's also going to make it pretty brittle, so probably not how we want it to go into service. So we need to follow the quenching operation with a tempering or stress relieving operation. So tempering is typically one particular operation. We can bring the part up to some intermediate temperature below the AC1, right? So now we're into those that second group of cycles that all happen below the AC1. So tempering can be any temperature, say from just a little bit above room temperature all the way up to any temperature just below the AC1, right? So for steels, that's going to be up over 1330 degrees. So that's a pretty big range that we have available to us. Unfortunately, we don't actually have that full range available to us for a couple of reasons. First, there's one particular segment of temperatures that if you temper in that range, you actually tend to make things more brittle. So when we were talking about the letter openers that you guys made, we were looking at tempering in a range up to about 500 degrees or just a little bit more than that. And then we said we would tend to avoid the range from, say, 550 up to about 800. That range generally is avoided because within that range, if you temper there, you get what's called tempered martensite brittle, or sometimes referred to as being blue brittle. So in most industrial practice, that range is avoided. But the lower temperature range, where we were using the letter openers, is widely used when you need high hardness. And then you can go above 800 if you need lower hardness and higher toughness.
What's the reason for the tempered martensite brittle then?
I knew you were going to ask me that. I don't have the answer off the top of my head, but you can find it in George Krause's book.
Okay.
actually have it marked in my book, I should have brought it with me.
Okay.
I have a sticky note there because I've looked it up numerous occasions. I think that's one of those phenomena that's, they have ideas about it, they're not 100% sure yet exactly why. These are things that often are related to what's happening at very, very small scale along grain boundaries. They talk about things like partitioning, phosphorus, and things like that. So these are the kinds of things that you would study with the TDF.
Is it similar to some of the like precipitation hardening that occurs with like chromium-based alloys? Maybe like a carbon at the grain boundary, and it actually hardens when you're tempering.
So I don't know that the improvement phenomenon is the same as that, but you can get secondary hardening. Is that what you're thinking of?
Yeah.
We can talk about that.
Necessarily related to.
Yeah, we'll talk about that. Yeah, no, I don't think it's necessarily an improvement. Microstructurally, and I know we tried to do this in one of the labs, and the images didn't turn out as good as we had hoped, but when you're tempering something, you're starting with a fully martensitic structure, in the case of our example, which is BCT, right? We trapped all the carbon in this matrix. The carbon wants to get out, it can't get out, so we have something that's extremely hard, right? But now if we put in some temperature, we've provided a little bit of energy to allow that carbon to diffuse out of that matrix and begin to form iron carbide again. As we get more and more carbon leaving the structure, this hardness goes down. The carbon tends to collect as little tiny spheres, and those spheres will arrange themselves in different ways. And so if we were able to do a study of microstructure versus tempering temperature and hardness, you'd be able to see how that changes, and you'd be able to see that something that's tempered at a low temperature, just a few hundred degrees, or maybe not tempered at all, say just in the as quench condition, looks very, very different from that same alloy tempered at 1200 or 1300 degrees, because it's got a lot more, a lot higher temperatures, so diffusion can happen faster, so more diffusion happens, and so the carbon is leaving the structure. You've got a much softer end result. Okay, so that was tempering. Talk about stress relieving as a separate operation from tempering. When you're making some parts, especially large, long components, and you go through the higher temperature heat treatment operations, you go through quenching, it's not uncommon that they will bend. Right? If I have a shaft that's several hundred inches long, and it's 10 inches in diameter, it's probably not going to be straight when I'm done with the quenching and tempering operation. But I need it to be straight. If I've got to put it into a machine tool, the machinist wants it straight. The customer is going to make, say, a ship shaft out of it. They want it to be straight. So we have to plastically deform it. We have to bend it back to being straight. Now we're not going to heat it up to a forging temperature to do that, because that would completely undo all of the work we just did in the heat treatment operations. But we will still bend it. Some alloys we can bend at room temperature, some alloys we have to take to some intermediate temperature, still below the tempering temperature, and we'll bend it. And when we do that, we put in plastic deformation, which means that we've actually increased the number of dislocations within the part. And sometimes we put a lot of dislocations in there. That means the result of that is that we have stress from plastic deformation in the part. So now I have a straight part, but it's filled with some stress. If I give that to my machinist, he goes and starts to take metal away, that's going to give an opportunity for that stress to cause dimensional change. And what will happen is the bar or the shaft will want to bend again. So we need to relieve the stress from the dislocations. That's what the stress relieving operation is. And we can use that. We have a lot of temperatures available to us for stress relieving. We find that in general, the minimum temperature that you're going to have much effect will be about 900 Fahrenheit. And any temperature above that will tend to be giving you better and better dimensional stability. So you have to balance the stress relieving temperature with whatever tempering temperature you use to get your hardness and mechanical properties. So generally what we'll do is, let's say I needed to make a part and get a tempered at, say, at 1150. If I tempered at 1150 to get my hardness and mechanical properties, I would probably do stress relieving at about 10 degrees. Stay about 100 degrees below the tempering temperature, and in that way, I'm unlikely to affect the mechanical properties, but I can still put enough energy in to allow those dislocations to realign themselves and relieve that stress. Questions on that? Okay. Remember I said that annealing is one of those things that has a lot of different subtext to it. And this is one of those. This one is actually one that occurs above the AC1 or the AC3. Solution annealing is done with alloys which tend to form precipitates. So you'll see this done in some stainless steels that are precipitation hardening. You'll see it done with aluminum alloys. You'll also see it done with austenitic and duplex stainless steels, where you have a tendency to form undesirable precipitates. So let's talk about that. If I have an austenitic stainless steel, like I say a 360, very common nickel chrome based steel, pretty good corrosion resistance. The chrome that's in there will have a tendency to want to form a chromium carbide with any carbon that might be present. Now, those grades, that grade in particular, has a fairly low carbon content. We're talking about, say, 0.00, 0.03, 0.04, so it's pretty low. But there is still some carbon present, and the chrome can react with that carbon to form a chromium carbide, just like it would in a low alloy steel. When that happens, the chrome is now tied up with the carbon, at least some portion of it is, and is no longer available to help with the corrosion resistance of the material. It's still physically present. If you did some analysis, you would still find it there, but it's not available to help with the corrosion resistance. So users of that material don't want that to happen. So what we do is we take the material, we heat it up to, in this case, it would be about 1900 Fahrenheit, and we're making sure to dissolve chromium carbides. And then we're going to quench, not because we're trying to form marcasite, but because we're trying to prevent the formation of the chromium carbide. We do the same thing in alloys where we get precipitation strengthening, which we'll talk about, I think, here in a moment. So solution annealing is done to put some constituent in solution and keep it there. It's probably the simplest explanation. In the grades where you do this, there are some that will form some marcasite, which we'll talk about in a minute, but all of the austenitic grades, the duplex stainless steels, those are grades that you're not going to be able to form marcasite. The alloy isn't there. You're doing the process just to dissolve undesirable constituents and keep them from reprecipitating. I mentioned those. Also, so duplex stainless, as I just mentioned, chrome copper alloys, and also nickel-based alloys can all be handled in this way. So I mentioned aging. So aging in certain alloys, we have a process where we first start with solution annealing. So these are alloys usually that have a certain amount of copper. Copper tends to form precipitates, and the precipitates can be advantageous. They act a bit like carbon in that, or I should say iron carbide, in that they put a strain on the matrix when they're present. So we're talking about copper contents in the maybe 2 to 4% range, not real high. So I can take, and if I have an alloy like this and it's got copper as an alloy element, I can heat it up, I can quench it, solution in the inlet, dissolve the copper, and at that point, the material is going to be as soft as I can make it. And if I follow that with a low temperature cycle, say 900 degrees or 1100 degrees, I will initiate the formation, the precipitation of the copper compound. When I do that, I increase the strain on the matrix, which increases the hardness and resulting tensile yield strength. So there's a few stainless steel alloys that are handled in this way, and they're commonly used in aerospace applications and others where you need relatively high strength stainless properties. With these materials, the lowest aging temperature typically gives you the highest properties, and as you increase the aging temperature, the tensile and yield strength and hardness goes down. The reason for that is because the size and distribution of the copper precipitates changes. At low aging temperatures, you have a very fine distribution of copper precipitates, and you have a fairly high hardness and strength because there's a lot of strain on the matrix. As you go to higher aging temperatures, those very fine particles can collect together, and so you'll have fewer particles, but they'll be larger. That actually results in a reduction in the strain on the matrix, and therefore the tensile and yield strength and hardness come down. Questions on that? Okay. We'll run through a quick overview of typical mechanical properties. Are you all familiar with this stuff already? Because if you are, I'll just skip that. So we'll run past that. You're all familiar with impact testing? Okay, good. Hardness testing, I know you're familiar with that. Tensile testing, how to read a tensile graph, you all know that, okay? Okay. You guys are aware that you can relate impact or relate hardness and tensile tests. You can convert from one to the next. Okay. And Sharpie test, you all know what ductile brittle transition temperature is? Okay. All right, let's talk a little bit about modeling and heat treatment then. So here's an example of a part that I hope you get a chance to see when you come to your tour. This is a part you can see here. This shadow is what the final profile will look like, and the blockier shape is what we've produced. So you can see that we've got lots of changes in the cross-section in this part. We've got some really thick areas here. We've got very thin areas over here. This is all open. This is a big counter, what we call a counterform. This is all forward shape. So the potential exists there to have cracking occurring. So there was, well, actually we modeled, we should back up a minute. Before we modeled heat treatment, we modeled the forging process of that because it is a complex shape. So we're able to figure out more accurately the total weight of the amount of metal we need for the part, plus the weight of the tooling and the forging, which influences and controls what kind of equipment we need to make it. And also allowance for oxidation, because this part is one which is made mostly, it's almost completely enclosed with tools, so we have to account for that scale as well. And here's what the part looks like. This is the view from one side. So I had a rather abrupt transition there. We were talking about heat treatment. Now we're going to switch over to some simulation stuff that is both covers forging, but also some on the heat treatment. I put the simulation stuff in the class because I wanted you to see how, as an industry, the forging world is using modern technology to enhance what they're doing, not just staying with the old way of doing things, although that has worked out pretty well, but as our customers put on more and more demands for what they need, we're taking advantage of the tools that are available, in the modern world, if you will, to help enhance Here's that same part from the other side. And you can see this is all the as-forged surface. So this form here was created by forcing a tapered punch into the ID in that part. So now that we have the part made, now we've got to heat treat it. Of course, we want to control the microstructure. We talked a lot about that. So we modeled what was going to happen at different points on each part. You can see this is a cross-section of the part, various positions, and then how things are cooling at various times here. Right? So we had talked about before about geometry testing and how we could look at geometry cooling rates and compare that to what's going on in a real part. Or I had said we would put thermocouples on a part and actually measure what's going on. But if I've made a big part, say, I might not want to drill holes in it because that might wreck the part. I mean, it might let me understand the process, but I might have to scrap the part. So modeling it will allow me to tailor and tune my process before I get to the actual production. And provided I've got the correct inputs, I'll have a good part that can go to the customer with no unwanted holes or cracks. So we've talked about this. I'm going to skip over this about cooling rate. We've got, this would be what you get off of the TTT curve. Of course, there's no temperatures or anything here, but you can see this particular curve shows two different noses. This would be your pearl-like nose, this would be your bainite nose, and this would be your Martensine thread temperature. Again, that's just a generic illustration. We can see what happens now as we cool. We've got the cooling curve for the surface, one for the center. So this lets us see what kind of structures we would have at this region of the part, and then at the center we're going to have, it looks like a mostly pearlitic structure. So if we did the modeling and we got this result, and we didn't like it, we could say, well, what can we change? Maybe we can change the cooling rate somehow by, if I wanted this to be over here, maybe I could change the cooling fluid, switch from polymer to water, or change the amount of agitation, right? Or maybe there's some way to change the geometry of the part. Maybe I need to combine some preliminary machining with that part to reduce the cross-section so I can shift this way. So mechanical properties, we skipped over that since you're already familiar with the testing. But we do know mechanical properties are dependent largely upon cooling rate during quenching because that's what's going to set the microstructure. And microstructure is what controls properties. We've got some variables. We've talked about all of those things already, so I'm going to skip past that. We talked about that we have stresses during cooling. If those aren't managed correctly, we can get cracked parts. We can also have changes in dimension. Here's another illustration. How things change during cooling. So we saw this or something like this earlier on. So here in this case, instead of having showing different alloys on the same graph, now we're showing different cooling rates of the same material on one graph, right? So here we have the fastest cooling rate, intermediate cooling rate, slower cooling rate. The slower cooling rate is going to have less variability along the diameter of the bar, but it's also going to have a lower starting hardness. I'm going to skip through this a little bit because we really covered those things already. So rough turning means that we're machining that part in advance of quenching. And the reason for doing that would be to reduce mass, but also to remove the oxide layer. You saw in the picture of that big funnel-shaped part a minute ago, we had a lot of oxide on that part. That's normal from forging. Well, that oxide layer is an insulator. So if I want to enhance the cooling rate, speed it up, I have to get rid of that insulating layer. So I would, machine that off. Now, it may be that I need to machine just a small amount to remove the oxide layer, or it could be that the geometry of the forging that I make is still got too much mass in it. It may be that that's all I can do from the forging standpoint, but I need to remove a lot of that mass, or maybe remove that mass in certain regions of the part through machining before I get to the treatment, so I have the proper cooling rate. Let's see here. Some of the things that affect mechanical properties besides cooling rate and quenching are segregation, chemical segregation. I think we talked about that in an earlier lesson on steel making. We have chemical segregation in ingots. We can also have non-metallic inclusions that can affect mechanical properties, and of course, the heat treat variables that we've already spent a bunch of time on. All right, that actually takes us to the end of the lecture. Are there questions on that? Kind of ran through the last bit really fast, but it seemed like that was all a review for most of you. Questions?
How close are your models to producing the microstructure that you did? So when you're looking at the temperature, can you pinpoint what microstructure you're going to get, or what's your error bars on that?
You know, every situation is unique. I was telling the students before you got in here that we have a situation we're dealing with right now where we model the job mostly because we were trying to do stress analysis so that we didn't have crack parts. And the model didn't show any dangerous stresses, so we went ahead and did heat treatment, and parts went out without further machining by us. The customer got out and they found that there were lots of cracks in the parts. So the models are only as good as the inputs, and every situation we deal with is unique. So what we try to do is do a model and then compare that to what we actually get. And if there's a difference, then incorporate that difference into the model so that it gets better over time. But we deal with so many different materials that, you know, modeling, we're pretty good most of the time with modeling, like say carbon or low alloy steels. We have a lot of experience with them, and not only we have a lot of experience, but the folks that create the modeling software have a lot of data available to them to give you a baseline to work from. But if you're dealing with something like a duplex thinking steel, you may be hard pressed to find good baseline information. And so I will say I'll give you a quick example of a part that we're working on. We actually have already heat treated it. It's kind of a neat part. It's a super duplex stainless steel part. It's a big circle like this, and it has 4 holes like this. And the diameter is about 96 inches. The hole diameter inside here is about 28, 30 inches. It's about 21, 22 inches thick. And the concern is that in this region here and here, the mass is, you know, say a 20-inch diameter ball in there, but the web here, which of course I didn't draw very uniformly, the web is only about 7 inches. So that grade doesn't undergo a phase transformation for quenching, but it does have the thermal expansion and contraction issues. And so there was real significant concern that we would crack this thin area. And so we did modeling and came up with a plan, and we executed and did crack. And we're all really excited because that was a part that was quite expensive and would crack. And we weren't really sure what else we would do. So we, definitely rely on modeling tools in those kind of situations. Any other questions? And I know folks were interested in taking a short break before the test, so it's time to do that. One thing I do need from somebody, it doesn't matter who, I need to give somebody a copy of today's lecture for Dr. Metallurgical. So anybody got a computer I can download this to while you guys are taking the test? Do that?